Please, if anyone can start recording. Okay. Today, inshallah, we will discuss the numerical solution of the swing equation. Actually, this part is more or less not related directly to power system. It is just mathematics and numerical techniques, but we need it in order to solve the swing equation as nonlinear differential equations. So we discussed earlier the graphical solution, which is the equal area criteria. And we know the limitation of equal area criteria, which is applied mainly for single machine infinite bus. But for multi-machine, although there are some trials to extend the equal area criteria to multi-machine, but still the equal area criteria is applied for single machine infinite bus. And also, if you still remember in these examples that we discussed an equal area criteria, the only example that we can calculate the critical clearing time is where we have a three-phase fault at bus. So the electrical power during the fault equal to 0. So we can calculate the critical clearing angle, and we can calculate critical clearing time by double integration. But other than this, it's very difficult to calculate the critical clearing time, which is a very important figure for power system protection. So today, inshallah, we'll see the numerical solution of the swing equation. So we will see the ordinary differential equations, numerical integration methods. We will see the Euler method, which is a very simple method, modified Euler method, which better than the Euler method, trapezoidal method. This is another numerical integration technique, and the Runge-Kutta method. We have second order, which is second order, which is a modified, and also we have fourth order Runge-Kutta method. So we will see the fourth order Runge-Kutta method, where you have 4 approximations to calculate the derivative. And we will see an example for modified Euler method, how to implement it. And also we will see an example with the trapezoidal method implementation. Many problems, including many in power area, can be formulated as a set of differential algebraic equations. In general, this is the general form: x dot equal to f of x and y. This is the differential equation, and this is the algebraic equation: 0 equal to g of x of y. The power example is transient stability, in which f represents primarily the generator dynamics, the swing equation, and g primarily the bus power balance equation. And you can have the dynamic model of the machine and also the power balance. If we expand this to multi-machine, we have load flow solution. A load flow is algebraic equation, load flow, and the dynamics of the machine. You can write the swing equation here. We will initially consider the simpler problem of just x dot equal to f of x, similar to the swing equation. Assume we have a problem of the form x dot equal to f of x with the initial condition here x0. This is known as initial value problem, since the initial value of the x is given at some time t0. We need to determine x of t. We need to find x of t here. So you can your initial value x0 must be either given or determined by solving of an equilibrium point. And you can definitely at steady state, this x dot equal to 0. At steady state, you can have x dot, this is equal to 0, equal to f of x. And you can solve f of x equal to 0 to find the initial condition if it is not given here. F of x equal to 0. Higher order systems can be put into this first order form. And usually if you have even x double dot, like we have here d square delta by dt square, we divide this to d omega by dt and d delta by dt. So we can, put the higher order differential equations into first order differential equations or first order form. Such as linear systems, and analytic solution is usually not possible. Numerical methods must be used. Many techniques exist for solving nonlinear ordinary differential equations. As we mentioned, Euler, modified Euler, trapezoidal, and others. Runge-Kutta method also. For the purpose of this discussion, we shall assume that equations are of the form x dot equal to f of x, and the initial condition x0 is given here, where x is n-dimensional, and this x is n-dimensional. You have x1 dot, x2 dot, and so on, up to xn dot. F1, F2, and so on. A typical power system application is to assume the power flow solution represents the equilibrium point. As we mentioned, the power flow or load flow problem is a steady state problem. So this is the equilibrium point. We have here g of x, y equal to 0. So back solve to determine the initial state variables x0, and this is what we will discuss in the next part or next class when we discuss the stability of the multi-machine system. We will see to analyze the stability of multi-machine system, we have to solve the load flow at the beginning to find out the initial condition. So the first step is to solve the load flow problem in order to study the stability of the system later on. This will be discussed in the next class, inshallah. At some point of contingency occurs perturbing the state away from the equilibrium point. The time domain simulation is used to determine whether the system returns to equilibrium point or not. Of course, if you solve the swing equation numerically, and if you get delta as a function of time, so you will see delta oscillating as such, so you can judge whether the system will go to regain its stability or will be unstable, and what is the equilibrium point at the end. So solving the swing equation gives you an indication of the system stability. The Euler method, which is the simplest method, consider the first order differential equation dx over dt equal f of x. Very simple. And the Euler method is illustrated as shown below, where the curve shown represents the solution x of t. Here you have a function. This is the x of t. This is the solution, x as a function of t. And if you start here with t equal to t0, the initial condition, so you calculate the derivative at this. You get the tangent of the curve at this point. You approximate the curve, you approximate this curve by linear around this point. So this is t0, and then you increase the time to delta t, and then you can increase the time, and then you calculate the derivative, again a derivative at this point, and you approximate the curve by a straight line between t1 and t2. At t2 you recalculate dx by dt at t2, and then you approximate it by a straight line here, and then you get t3. And of course this is an iterative method. With each iteration you increase the time by delta t, and you calculate the derivative and you approximate it as such. So actually Euler method is very simple. Euler method is simply approximate delta dx by dt as x of k plus 1 minus x of k over delta t. Okay, so x of k plus 1 equal to x of k plus delta t times f of x. So when you start with at t0, you know the function equal to x0. So this is x0 is known, and delta t, you can calculate f at x0, and you multiply by delta t, and then you can get x of k plus 1. And then when you have x k plus 1, طبعا هنا ال k equal to 0, here k equal to 0. So this is x of 1, and then you can get x of 2 equal to x of 1 plus delta t multiplied by f of x calculated at x1. And then x of 3 equal to x of 2 plus delta t multiplied by f of x calculated at x2, and so on. So iteratively you can continue until you reach to if you want to solve مثلا, for example, from 0 to 2 seconds. So and you have delta t equal to 0.1 second. So how many iterations we will do from 0 to 2 seconds with 0.1 second iteration or interval? Then you have 20 iterations. So you go up to x20 here. Okay, so in a swing equation, for example, you need to solve for time between 0 to 5 seconds. So if you set the interval 0.1 second for 5 seconds, so you need to carry out 50 iteration in this case. In general, the smaller the delta t, the more accurate the solution. You can see here in the solution calculated here is a little bit behind the actual value. It goes below the actual value. So in order to improve the accuracy, you need to have delta t very small. If you decrease the interval here, delta t, it will give you good accuracy. And in some cases, if delta t is not wisely set, you can have numerical instability. So the solution is diverged, and starting with the initial point t0 x0, the curve can be approximated by the tangent evaluated at this point. For small increment t denoted by delta t, the increment in x is given by delta x equal to the f of x or dx by dt calculated at x0 times delta t. So this is the slope at this point. And then recursively, the value of x at t0 plus delta t, x1, equal to x0 plus delta x. And this is delta x here. And this is f of x. So you calculate it at x0 and multiply by delta t. And then iteratively you can continue until the final time that you need to solve. So the above approximation is the Taylor series expansion of x around the point where higher order terms have been discarded. And this is the Taylor series expansion, but we discard the second order term, third order term, and higher order terms. So we approximate x dot just by the first derivative here. The subsequent value of x can be similarly determined, x2, x3, and so on. And the computational algorithm is as such: xi plus 1 equal to xi plus dx by dt delta t. By applying the above algorithm successively, we can find the approximate value of x of t at enough points from an initial state to final state. You need to solve for a final time, 5 seconds or 3 seconds or whatever, then you can continue until you reach to the final time. So the algorithm is simply can be set as such: t0 and x0, this is the initial point, big the time step delta t, which is the problem specific. Of course, if you experience low dynamic, then delta t could be high. If you experience a high dynamic problem, then delta t must be very small. Like in a swing equation, for example, in a swing equation, we approximately use delta t equal to 0.001 second or 0.005 second. More than this, you can face some kind of numerical instability or divergence. So this delta t, you set it, and then while t is less than t final, you can do this: x of t plus delta t equal to x of t plus delta t times f of x calculated at x of t. And you increase the time and then you loop here until you reach to the final time. Is it clear? Consider this very simple example in which we need to emphasize on the selection of delta t and how delta t can affect the in this very simple example, x dot equal to minus x equal to minus x, then this has a solution of x of t equal to x0 e to the minus t. And this is very simple. That's the solution here, x of t. And this is the exact solution, a closed form solution. So if you need x at 5 seconds, then you can substitute t equal to 5 seconds. At 10 seconds, you can substitute at 10 seconds. This is the closed form solution, and then a very simple problem. You can easily solve it. Since we know the solution, we can compare the accuracy of Euler's method for different time steps. And you can say if we start applying the Euler method, and this is the exact solution that we have. So let us compare between the Euler method and the exact solution for this very simple example. T equal to 0, 0.1, 0.2, 0.3, delta T here equal to 0.1 second up to 2 seconds. So if you substitute in the closed form solution, you will find out that, this is the solution, or this is the exact solution. If you take delta T equal to 0.1 and you implement Euler method, in this case you can have, this is 9 here, which is somehow less than this, 8.1, 8.8, 1.22 at the end, 1.35. So it gives you, as you can see here, not exact solution, of course. Definitely, it will not give you the exact solution. But if you select delta t equal to 0.05, which is less than delta t, you end up with the solution which is better than 0.1 second interval, close to the exact solution. So delta t plays a great role in the accuracy of the solution. So you need delta t to be very small. Any question? Any question?
Not what about operations?
What about?
Talking about delta t playing a very big role in the accuracy of the solution. I think the number of iterations as well also play important role.
Definitely, if you have not a number of iteration. Number of iteration depends on delta t. Number of iteration equal to t final over delta t. If you want to go to 2 second final time and delta t equal to 0.1, so number of iteration here equal to 2 over 0.1, so 20 iteration. For this, In order to reach to 2 seconds, you need 40 iterations.
Okay.
So, definitely, number of iterations depends on delta t. And we are targeting a final solution here, a final time. Ahmed Suleiman Qanas.
Yes, doctor. Doctor, I have a question. Always, if we decrease delta t, the accuracy will improve, or is there some limit to the Euler method?
لا. If you decrease, or if you set the interval smaller and smaller, you will get more accurate and more accurate solution. But of course, this at the expense of time. This is at the expense of computational time.
Okay, noted.
Of course, if we try delta t equal to 0.01, we will get better solution than this. We will get it very close to or closer to 1.53. Okay. But this, of course, at the expense of the computation time. And you have to compromise between this and this. Actually, in MATLAB, it uses some kind of adaptive delta t. In MATLAB, in ODE, you have ODE function, ODE 3.4 or ODE 4.5. So these are the function in MATLAB to solve ordinary differential equation 4.5 مثلا. These are uses these functions use an adaptive delta t. So at the beginning, maybe assume that this is the solution here. As you can see here, at the beginning, you have here high oscillation. So you can decrease the delta t here to 0.001. Once you experience in the solution doesn't change very much, you can increase delta t to مثلا 0.1. And if it comes to this, you can increase it to delta t equal to 0.2 seconds, and so on. So it depends on the solution. You can have an adaptive delta t, and this is what you have in MATLAB function to solve the ordinary differential equation. Okay. So this is the Euler method. Very simple, but not accurate unless you have a delta t very small. Another example, you have x1 dot equal to x2 and x2 dot equal to minus x1, assuming the initial condition x1 of 0 equal to 1 and x2 of 0 equal to 0. Again, you can have here some kind of, closed form solution. And you can compare if you implement Euler method with this one. Of course, you can write here x of x1 minus x1 0 equal to x2 of s, and x2 of s minus x2 0 equal to minus x1 of s. Of course, you can say, for example, and you can have x2 of s, you can substitute it here. Let us take x2 of s here. This x2 of s equal to x1 of s minus plus x2 0 over s. You can substitute it here and you can get, for example, x1 of s. You can solve for x1 of s and x2 of s. You can solve for this. The analytic solution is x1 of t equal to cosine t. Probably x1 of s here, you will end up with s over 1 plus s square, or s square plus 1. S over s square plus 1. This is the inverse Laplace will give you cosine t. So this is a closed form solution. This is a closed form solution that we have. If you need to calculate the time at 10 seconds, you just substitute cosine 10. This is of course in radian. 10 here is not in degree. 10 should be in radian. And then you can get cosine 10 at 2 seconds, at 1 second, whatever. So this is the closed form solution of this. We can again compare the results of the analytic solution and the numerical solutions. You can have here a table again with the starting from the initial conditions at t equal to 0. And next calculate x of t at time t equal to 0.25. The interval here equal to 0.25. So this is delta t. So you can get x of 1 equal to x of 0 plus a delta t multiplied by f of x, which is xt, x2 here. F of x equal to, this is dx by dt, and this is f of x. So x2 of 0, and it's given here. X2 of 0.25 equal to x2 of 0 minus times x1. So you can get x1 and x2, and then you can proceed for x1 of 0.5, x2 of 0.5, 0.75, and so on. So this is x1 of 0.5 gives you this value, and x2 of 0.5 equal to 0.25 minus 0.25 times this. And you can iteratively solve for x1 and x2. This is the situation. This is the t, 0.25, and so up to 100 seconds. So we solve for up to 100 seconds. We know x actual solution. If you substitute t equal to 0, so cosine equal to 1, 0.25, 0.5, 0.75, and so on. You have here at 10 seconds. If you substitute of 100, then you substitute as such cosine 100. 100 is in radian, so you can get it as such. So this is the actual value, and this is the Euler solution for delta t equal to 0.5. You have it here 1 up to, and you can see here that this is the numerical instability. Then you have, this is cosine t, and you know cosine t is plus minus 1. This is the range of cosine t. Now you have the solution equal to minus 3.1 or minus 100. So instability, you experience here instability in the solution. So delta 0.25 is very high value. You have to reduce it to whatever. You can check 0.15, you can check 0.1, and so on. So as you can see here, this is the numerical instability as we mentioned. If you set the delta t is very high. Since we know from the exact solution that x1 is bounded between -1 and 1, clearly the method is numerically unstable due to the high value of the interval. Okay, so below the comparison of the solution x1 of t at t equal to 10 seconds, delta t, this is the actual value, x of 10, x1 of 10, this is the exact solution. And if you take delta t 0.25, you will end up with this solution, which is numerically unstable, as we mentioned. For 0.1, again, numerically unstable. When solution is bounded by multiple plus minus 1. If 0.01, you get it minus 0.88, which is very close to this. And even if you reduce delta t to 0.001, you end up minus 0.84, and this is 84 approximately. So you almost get the exact solution, but at this time step, small time step. Is it clear? Omar, Sulaiman. Salman, Omar.
Yes, I wanted to ask, the numerical instability that occurs in the Euler method is it same thing as divergence? Like I would say that, okay, the solution diverge or something.
Diverge, yes. The solution diverge.
Okay, thank you.
طيب, let us stop here for Maghrib prayer 5 minutes, and then we will come back. Okay? السلام عليكم. Okay, before starting, and I would like to discuss with you the midterm exam. Do you prefer to be online or in person?
I like doctor to be in person.
In person?
Yes, for me, it's my preference is to be in person.
For me also, doctor, in person.
Mm.
In person, doctor, in person.
Yes,
I
doctor,
agree.
in person also.
Okay, great. طيب at what time? لأنه we need to reserve room in advance, and tomorrow is the last date to reserve a room. So we have to set the time and date. So what do you think? Today is 1 March. So this is week number 7. So if we say after 2 weeks, then you are talking about March 14, March 15. This is Monday. And what do you think? And I would like to make it on I don't know. Then on Monday or Tuesday, it's difficult. Monday, Wednesday is difficult. You know, I have another class after this one. So we need to make it either Thursday or Sunday.
Doctor, can we shift it 1 week?
Hmm?
To shift it 1 week instead of 15, we can make it 22nd. 15 because in 15 we have planning midterm.
15 you have planning.
So we can make it 22nd.
22nd is Monday.
Monday.
Or 20, doctor, on
Hmm?
Saturday.
Yeah, Saturday.
20th of March.
Saturday is okay. Saturday 20. That's okay. Saturday, March 20. Saturday. At what time? Saturday. Maybe after Dhuhr prayer مثلا.
At 1 o'clock, maybe it's good.
Saturday at 1 o'clock. March 20. Okay, great. So March 20, Saturday, 1 o'clock. Okay?
Okay.
Doctor, is it online or physical attendance?
Physical. In person.
طيب, what is the material for the midterm?
Until we finish. And when we finish, then we can see what material covered until the exam. So still moving forward. We have multi-machine, we have fax devices, we have this. All these will be covered before the exam, inshallah. Okay. just to document it. Okay, let us discuss the modified Euler method. We have like very short quiz will come up soon. Be ready for this. Modified Euler method. The standard Euler method results in inaccuracies because it assumes that the slope is constant over the entire interval, causing the points to fall below the curve. This is already discussed. An improvement can be obtained by calculating the slope at both the beginning of the interval and the end of the interval, and we can get the average. So in modified Euler method, we calculate, we say x1 equal to x0 plus df by dx calculated at x0. We calculate at x0, we get x1, and we use x1 to calculate again df of x at x1. So this is the at x0 and this is at x1, and then we can get the average, 1/2 of df by dt at x0 plus df by dt at dx at x1. So we can get the average here. The quiz started already.
Doctor, quiz number 4.
Quiz 5.
No, not appeared yet. 5.
I can see it, Doctor.
You can see?
Yes, I can see it.
Okay, خلاص يبقى started.
time was
Okay.
very fast, Doctor.
Huh?
Time was not enough.
يا راجل ده two very simple questions يعني ما فيهم calculation ولا حاجة.
They were easy, but the answer of the first question need to approximate. So I guess the approximation maybe makes a difference.
أنا قلت لك approximated to linear يعني straight line. وبالتالي very simple. Doesn't need any يعني integration أو calculation أو حاجة يعني very simple.
It was simple, Doctor, but it was a matter of graphing or curving the drawing.
مش محتاجة والله. طيب على العموم خلينا نشوف. بس it seems إنه your performance all يعني your performance is not that good يعني. أنا شايف يعني كله درجات يعني مش عارف. خلينا براجعهم واشوف كده.
Doctor, how can we know our mistake? I mean, if we can see the answer.
Yeah,
Yes,
I will show you the answer. بس أنا عاوز أشوف السر.
Yes, doctor.
أنت لسه بادئ الكويز؟
Yeah.
ليه؟
I was praying.
لا ما احنا بريدة احنا من البريدة بقاله يعني احنا كنا بدأنا البراير من 5:57 والكويز 6:12 دقيقة.
Should I stop it now, يعني?
لا you should stop طبعا of course.
Huh?
Yes you should stop it. لأنه يعني أنا ممكن أحط طبعا ليميت لأنه الكويز يبقى افيلابل امتى، انما انت بعد ما الناس خلصت الكويز وجاي تبدا الكويز بعدها لا it's not fair طبعا.
Okay, no problem.
Okay.
Also, please, the solution to this quiz. I don't know what happened.
Huh?
This quiz. I scored 0.
Yeah, you scored 0 طيب. So I will release the answers, but don't يعني waste your time now for the answers also. يعني you can show it later or see it later يعني and you can review it later يعني. Okay, let us continue for modified Euler method. This procedure is known as a modified Euler method. Sometimes it's called the second order Runge-Kutta method. Second order Runge-Kutta method. And it uses here two approximations to calculate the slope at the beginning and at the end of the interval. So by using the derivative at the beginning, the value at the end of the step equal to is predicted from this. You can have x1 equal to x0 plus calculated and this. And then you can calculate dx by dt at x1 predicted at this value. So you calculate it at x0, and then you calculate it at x1 predicted, and then you can get the derivative, the average. So you can get the average, and then you can say x1 corrected, and we have a predicted value, and then we correct it. So x1 corrected value equal to x0 plus 1/2 of the average slope here of x0 and x1 predicted times delta t. So this is the modified Euler method, which is more accurate than Euler method here. So in recursive form, you can write x corrected I plus 1 equal to xi plus 1/2 equal 1/2 times the derivative at xi, derivative at xi, 1 I plus 1 predicted times delta t. So as you can see here, for each calculation of xi plus 1 corrected, you need to calculate xi plus 1 predicted first, which is equal to xi plus 1/2 or plus d by dt at xi, and then you get xi corrected. So you need to calculate predicted value and then you correct it here. So this is what we have done here. You calculate the predicted and then you calculate the corrected value. So 2 steps in order to find the value of the function at any interval. So this is طبعا, of course, in terms of computational time, will be, will take more time, but definitely the accuracy of the solution is better. So the accuracy of the method depends strongly on the integration interval. Again, the step size must be small enough to obtain a reasonably accurate solution, but large enough to avoid numerical limitations of the computers. Numerical errors is introduced by discarding the higher order one, of course, and this is again Euler method. We neglect all the higher order terms of the Taylor series expansion. So this is some kind of approximation. Modified Euler method is sometimes called second order Runge-Kutta method. Consider the system example again with this example that we discussed earlier, and we know the solution is x1 equal to cosine of t. Let us implement this with delta t equal to 0.25 and t equal to 0. So this is the initial condition, and this is the value, and x of 0 plus k1, this would be x1, and k2 equal to 0.25 f of x0 plus k1, derivative of x1 predicted here, and then you can get x of 2, 0 equal to x0 plus 1/2 times the f of x calculated at x0 and f of x calculated at x predicted value. So you end up with this value. So you calculate the predicted and then you calculate the corrected value. So this is the time. Again, delta t equal to 0.25 up to 100 second here or 10 seconds. This is the actual value. It is, as you mentioned here, bounded by plus minus 1. And this is for Runge-Kutta method, the second order or modified Euler method. You can see here, the results is much better than Euler method. In Euler method, we have this equal to minus 151 or something like this. So it is almost, it's okay, reasonable. And it gives, of course, the one, as the time increases, definitely you have the accumulation of error. Again, for the effect of delta t, this is the actual value, and if this is 0.25 at 10 seconds, this is the value, which is a little bit far from this. For 0.1, which is very close, 0.01, which is very, very close, and 0.001, exactly the same. So it gives you the exact value. So that means modified Euler method is much better than Euler method, but it needs more calculation. Modified Euler method requires twice the function evaluations per iteration, but gives much better results. The smaller error allows for larger step size compared to Euler method. In this case, of course, if you would get an accurate solution, so you can relax a little bit the interval, and you can increase the interval, and that gives you better results. Trapezoidal method, which is very simple. If this is the function, you can approximate the function between x and t plus h, or which delta t, h or delta t the same. So you can approximate the function here as a straight line. So if you have the integration to solve this function, you need x of t. So you integrate here. Well, integration here is the area under the curve. And if you approximate this as a straight line, so you can easily calculate the area under the curve. Here, this is delta t or h, and this is the value f of n, and this is the value f of n plus 1. So the area of the under the curve, this area equal to f of n plus 1 plus f of n over 2 multiplied by h. So this is the integration. This is the solution of this function here. So you approximate the area here of the curve as a linear straight line, and then you can get the integration very simple as a trapezoidal part here. So the integration from t to t plus h, or from t to t plus delta t, equal to an integration of this, which is h over 2 multiplied by the function at t and the function at t plus h. T plus h and the function here at t. So this is the, so you can easily here write x of t plus h equal to x of t plus this area, this trapezoidal area. So you can recursively write x of k plus 1 equal to x of k plus h of t, h over 2, or delta t over 2, multiplied by the function at the beginning and at the end. So x of n plus 1 equal to xn plus h of 2 f of n plus 1 plus f of n. This is an easy method and very popular for stability studies due to its numerical stability. Runge-Kutta method, modified Euler method, is called the second order Runge-Kutta method. We have also fourth order Runge-Kutta method, which is you calculate the function at n, you calculate the function at the second of the approximation here. You have a third approximation, fourth approximation. You calculate all these values, and then you calculate x1, x2, x3, x4. These are the slopes at the beginning approximation, the mid step. So at the mid step, and then again you have a slope at the end of the time, and then you can write x of n plus 1 equal to xn plus delta t over 6, k1, 2, k2, 2, k3 plus k4. So you can use also this Runge-Kutta method to solve the swing equation. Runge-Kutta method gives much better results, of course, لأنك أنت Second order Runge-Kutta method or modified Euler method, it gives it uses 2 approximations. Here you use 4 approximations. So for delta t equal to 0.25 and up to 100 seconds, this is the actual value for the same example. And this is the Euler method or modified Euler method you can see here, which is not accurate. But if you use Runge-Kutta method, 4th order, even with delta t equal to 0.25, you end up with approximately very close solution, 0.86, and we have here 0.86 as well, minus 0.839, minus 0.839. So Runge-Kutta method, 4th order, gives you better results, definitely. It's very popular for stability studies. 4 evaluations of the function per step is required. This is the drawback, and this is the disadvantage. And you need 4 calculations in order to get the function value at the end of the step. Okay, let us see this example for the application of modified Euler method. Assume that this is the swing equation, and we put it in 2 first order differential equations, and you can write here this is Bm minus Be, which is the acceleration power, and this is the delta by dt. Applying the modified Euler method, you can write here the predicted value of delta omega equal to delta omega of I plus calculated at delta I delta t, and then you can do again for the delta predicted value, and then using the predicted values you can get the derivative at the end of the interval. You can get the corrected value. You can get the slope at the end of the interval having this value and this value. So you can use these values to get the corrected value here. Delta omega equal to delta omega I, 1/2 of the average slope times delta t, and also delta corrected at step I plus 1 equal to delta I plus 1/2. Again, the average slope multiplied by delta t. The trapezoidal rule can be applied to the differential equations of the machine as follows. This is the application of trapezoidal method. xn plus 1 equal to xn plus delta t or h over 2 multiplied by the function at the end of xn, fn, and fn plus 1. D omega, if you want to apply this on the swing equation, we have d omega and d delta by dt. Assume that f equal to f1, f2. This is f1. This is f1. And this is f2. Then f1 at a step n equal to omega s over 2h on bm minus be of n. And this one also, f1 of n plus 1. Of course, this is the calculation of at n plus 1. The time here will be replaced by n plus 1. And we have only be as a function of time. All these are constants. f2 of n, which is omega minus omega s. f2 of n, you calculate the speed at n. Omega s طبعا اللي هي synchronous speed, which is constant, 1 per unit, or 377 radian per second. So omega s is known. So F2 of n plus 1, you calculate the omega at n plus 1. Applying the trapezoidal rule, omega n plus 1 equal to omega n plus h over 2 multiplied by f of n plus 1 plus f of n. F of n plus 1 plus f of n. This is f of n plus 1 plus f of n. You have here 2bm minus be of n minus be of n plus 1. And of course, you can write the same for delta. Delta n plus 1 equal to delta n plus h over 2 multiplied by, you have here f of n plus 1 plus f of n, which is omega n plus 1 plus omega n minus 2 omegas.
Doctor, thank you.
Okay, خلاص, let us stop here and continue next class inshallah. Ayub Khalifa.
Yes, Dr. Katab.